Hello again, Math 134 students. Let's do the recording of section 7.3 as well. This is also about trigonometric, but it's trigonometric substitution method. It's a technique of integration that it's summarized in this table. I like this table a lot. It's like summarizing everything you need. But let me explain things on the table and also give the reasoning behind everything here. So first, I don't like that there is root here. It's not the case that when you only have root of these terms, you use them. For example, when you want to integrate 1 over 1 plus x squared dx, something like this. It's in this form, some number plus x squared, but you don't see any root. For this also, you should use this. So because it's not only restricted to root, let me just drop out these roots. Usually we have root, but not always. When you see terms like a squared minus x squared or a squared plus x squared or x squared minus a, you use these tables. Similar to section 7.2 that I gave you the rules, and I said that you can memorize them if you like. But I mentioned the reasoning if you forgot the rules, how you can find them. So the idea here is the same. So either you can memorize that whenever you have this, you use x equals a sine theta. Or whenever you have this, you use this. And whenever you have this, you use this substitution. Either you memorize them, or if you want to understand what is the idea behind it and why this works, it's very simple. It's coming from the two identities that we discussed in the previous lecture. If you recall, one of them was sine squared plus cos squared. Let me use theta instead. Plus cos squared equals 1. If you move one of the terms to the other side, let's move sine. Then you get this identity. Cos squared is 1 minus sine squared. So I see that if I have a constant minus something squared, it looks like this. A constant minus something squared. That's the idea that why I use sign substitution, because I have a formula for this, which is given by the square of cosine, and that square, especially when we have a square root, cancel a square root. What other formulas we have? If you remember, the other formula that we had was 1 plus tangent squared is secant squared. So to be consistent for all of them, let me write the term 1 minus something or 1 plus something always on the left, and write the results on the right to be all similar to each other. So I have another identity that I have was 1 plus tangent squared equals secant squared. So if I have a constant plus something squared, I use secant. So when I have constant plus something squared, I use tangent as my substitution. I use tangent as my substitution to get 1 plus tangent squared or constant plus tangent squared, and I use this identity to write it as secant. So if I have constant plus something squared, I use tangent. Similarly, the same equation, if I move things around, if I move this 1 to the other side, I get secant squared minus 1 is tangent squared. I just moving this 1 to the other side of equality. You get secant squared minus 1, it's tangent squared. So if I have something squared minus 1, that thing is good to be taken as secant. So I can use this equation and write it in terms of like tangent. So if I have something squared minus constant, I use secant substitution. That's the idea behind them. And you may ask why we have these A's. It's to actually get one, not any constant. For example, for this one, let me explain it. A squared, let me do that computation here. I have a squared minus x squared. I'm I want, my goal is to use this. It's similar to not this because it's not constant plus something squared. It's not something squared minus constant. It's constant minus something squared, which is this one. So I want to use this, but for this one, I have 1 here. It's not a squared. To get 1, I factor this extra coefficient that I have, extra constant that I have. I factor a squared. Then I have 1 minus x squared over a squared, which can be written as a squared 1 minus, if I want to write this similar to this as something squared, that thing squared is x over a. So this suggests me, look at this, 1 minus sine squared should be 1 minus x over a squared. So this suggests me that the change of variable that I should do is x over a to be sine theta, to convert this into this. So that's the substitution that I need. If you move a to the other side of equality, you get that x is a sine theta. So that's how you get it. I did it for only one of them. For the rest is the same. You factor a squared, you get 1 plus something squared, and that thing which will be x over a should be tangent. For this also the same. Factor a squared, then you get x over a squared minus 1 times, of course, a squared, and the x over a should be secant. So either you memorize that in which situation what substitution you need to know, you need to do, or you understand this process. I would suggest definitely to understand this process. Why? You see in the activities. For one of the activity questions, it's not exactly this. But if you understand the thinking process that I explained, you can still do that activity. If you 100% rely on these formulas, you will stuck at that activity and you can't continue. So that's always, it's better to understand the reasoning, understand the idea behind it. Anyway. So we have this substitution. Now you completely know why these terms, seeing these terms is good because they are similar to these identities. And why this substitution works, because I want to write this as like 1 minus something squared, and that thing should be replaced with sine. And that's where this substitution come from. The same for the rest. Now that you know that, let's discuss about something which is called reference triangle. Do you remember when you do U substitution at the end, you don't leave your answer in terms of U. You need to substitute back U in terms of X. Here I'm doing some substitution. That new variable is called theta. At the end, you will have the answers in terms of theta. But that's not good. You need to replace all theta answers in terms of the original variable X. This is where it comes helpful. So this reference triangle is very simple. It's coming from this. Actually, it's better to view it as the way that I found it. This is the same as x over a is sine theta. This is the same as, let me write it as sine theta. It's x over a. If you remember, I'm explaining how this triangle is created. Definitely, even if you memorize these substitutions, don't memorize them. That's the worst case to do that. Definitely, you will confuse it in the exam. You don't need to memorize this. How do we get it? By creating the right angle triangle with one angle theta and using this substitution. The substitution says that sine theta is x over a. What is sine theta in a right angle triangle? It's opposite over hypotenuse. So if I take this to be opposite, this should be hypotenuse. So let's take this to be opposite and this to be hypotenuse. Then what is the last side, the other side that I don't have it? Use just Pythagorean theorem. This is hypotenuse squared minus the other side squared. That would be this side squared. So that side is a square root of this. So this triangle is created like this. Definitely don't memorize it. Create it from the substitution that you have. This is not always x or something as well. Sometimes you need to do a substitution like this. For example, x minus 3 over 5 is, for example, tangent theta. Then, if you memorize this triangle, it doesn't help you. You need to create the triangle for this. What would be the triangle for this? The angle, if you have a right angle triangle, angle theta, that's a small practice problem that we are doing. Tangent theta is opposite over adjacent. So if this is opposite, this should be adjacent. So if opposite is x minus 3, adjacent is 5, and the hypotenuse, you can find it by 5 squared 25 plus x minus 3 squared. That's how you should get it. Definitely it doesn't come, but by the way, this is hypotenuse squared. The hypotenuse is a square root of this. It's not coming from this exactly. It's not x here. So it's better to understand what's going on. Anyway, so you can create this and this triangle the same. Now, the final thing to discuss, let me discuss what are these sides that we found. So if you use the fact that we use the identity such that x equals a to become like this, if you substitute this in this, what do you get? You get that this term a squared minus x squared. It is a squared minus a squared sine theta. Sine squared theta. I just replace x with a sine theta. That's what we get. Factoring a squared, what you get is 1 minus sine squared theta. And that's why we did this substitution, to use this identity. And when you use that identity, you get a squared cos squared theta. So this side of the triangle, which is absolute value, root a squared cos theta, it is root of this, which is a, by assumption a is positive. And then absolute value cos theta. A similar thing happens here. If you substitute a tangent in this, you get a squared plus a squared tangent squared, factoring a squared. Let me write less and do it here. Factoring a squared, you get this. And that's why I did this substitution, to use these identities. And let me also use theta everywhere in these identities rather than x. Okay. Then 1 plus tangent squared is secant squared. Using that identity, that is a squared secant squared. So this term, it's root of this, which is a absolute value secant. The same here. If you substitute this in this, you get a squared secant squared minus 1. But secant squared minus 1, that the whole point of doing this substitution is to use that. It's secant squared minus 1 is tangent squared. So a squared is tangent squared. And this side is root of this, which is a, because a is positive, absolute value tangent. That's what we have. But very important point is that under these domains of theta that we have, let's see what happens. For example, for a unit circle here with cos here, sine here, when you are in this range, minus pi over 2 up to pi over 2, you are in this part. And you have absolute value cosine. But in this red part, cosine is already positive. It's not negative. So you can drop absolute value. That's a very important reasoning here, that because we are in these two quadrants and cosine is positive in those quadrants, this is actually a cos theta. That's coming from this. Let's do the same reasoning for the rest. Let me recreate my unit circle. Which is this. And now look at this domain. Oh, by the way, this is the same domain from negative pi over 2 to pi over 2. The only difference is that this does not include the endpoint. This includes the endpoints, but it doesn't matter. At the endpoints, there is no sign. These are just 0. So what happens here? I have secant, which is secant is 1 over cosine. So the sine of secant is the same as cosine. So when I'm here, cosine is positive, 1 over cosine is positive, secant is also positive. So this is actually positive a secant. I don't need absolute value. And finally, for the last one, if I again create an empty unit circle, the domain is between 0 pi over 2 and between pi and 3 pi over 2. But I have absolute value tangent. Absolute value tangent, it's positive in quadrant 1 and 3. It's negative in quadrant 2 and 4. So in these parts, tangent is positive, no matter you are in quadrant 1 or quadrant 3. So I don't need absolute value. And I can write this as a tangent theta. You can just memorize this as a rule that for these substitution that we are doing, whenever you get absolute value of the other term, when you do substitution sign and you get absolute value cosine, you can drop it. Drop absolute value. When you have tangent, you get absolute value of the other term secant, then you can drop absolute value. And when you do this substitution and you get absolute value of tangent, you can drop absolute value. Basically, you can ignore absolute value in these substitution methods under these domains. Okay, that's all the lesson. Now we can go over the exercises. So first one is this. I want to see what substitution I should do. So look what term I have. I have something squared, which is x squared, plus a number, plus a number. Which of the identity was something squared plus a number? For the last time, you need to memorize these identities. Uh, Something squared plus a number, it's the tangent one. So I need to use the tangent substitution. So because if you want to recall, 1 plus tangent squared is secant squared. That's the key identity that I want to use. And this is also, if you like, 4 plus x squared. It's a number plus something squared, so I need to use tangent. But not tangent itself. If I replace tangent in this, I get 4 plus tangent squared, not 1 plus tangent squared. To get 1 plus something squared, I need to first factor 4 out of this. Factoring 4 out of this, I get 1 plus x squared over 4, which is the same as x over, let me write first x squared over 4, and next step write it as x over 2 squared, which is the same as x squared over 4 is the same as x over 2 squared. This is in the form that I want. It's 1 plus a package squared. What is that package? It's x over 2. But that package, it's good to be taken to be tangent theta to use this identity. So the substitution that I need to do is x over 2 to be tangent theta. That's the same as x to be 2 tangent theta. So that is the correct answer. Or you can just memorize it. Memorize this table. That, oh, I have a squared plus x squared. I do x equals a tangent theta. If you want to use your memory to answer this question, you see that, oh, a is 2. This is 2 squared plus x squared. A squared plus x squared. So a is 2. And this, for this one, I need to use tangent. So it's x equals a, which is 2 tangent theta. That's if you rely on your memory. If you don't rely on your memory, that's the thinking process. That's why this substitution works. Even if you want to memorize, you need to understand this thinking process. Because there are some questions, the last activity that we do today, the formula doesn't help you directly. So you need to do this process to find a good substitution. Okay, now let's do the next question. So in the previous question, we have already seen that that's the same question as previous question. We have seen that x equals 2 tangent is a good substitution for this integral. Now I want to do the substitution. So if I want to do the substitution, I need to replace everything in terms of theta. So one of them is dx. Let me find the dx. If x is 2 tangent theta, dx is 2 derivative of tangent secant squared theta d theta. So in this integral, this is 2 secant squared theta d theta. And this is, if you remember, x squared plus 4. That's x squared. That's the same. I will do the computation again, but that's the same computation that I did in the table here to get these absolute value terms. And then I did some reasoning that absolute value is redundant. That's the same computation. So that's x squared, not x squared, I'm replacing with 2 tangent theta. So that is 2 tangent theta squared plus 4, which is 4 tangent squared theta plus 4. If you factor this 4, you get tangent squared plus 1. I use that identity. 1 plus tangent squared is secant squared. Okay, but what do I have here? It's root of it. So this is the same as, if you like, let's do all these computations in the next step. It's 5 over dx was 2 secant squared theta d theta. And in the denominator, I have root of this, root of x squared plus 4. But x squared plus 4 after the substitution is 4 secant squared. So it's root 4 secant squared theta. So root 4 secant squared, it's just 2 absolute value secant theta, 2 secant squared theta d theta. That's what we have. The reasoning. For all these substitutions, no matter it's tangent substitution, sine substitution, or secant substitution, under the domain that we discussed, you can drop absolute value. So this absolute value is redundant. I can drop it by the same reasoning that I did on the unit circle. Now I can simplify 2 cancel 2, one of the secants cancel one of these secants, and you get just 1 secant theta. So you get integral 5 secant theta d theta, which is option A. After the substitution, it will be simplified to this. Now, next question. I'm given that I'm doing this substitution. Assume that you did the computation until the end and you have some term like secant theta. You need to substitute back this in terms of x. That's the question. How do you express this purely in terms of x? How should I do it? By a reference triangle, by creating the reference triangle. Note that I don't memorize reference. Even if you memorize the substitution ones, don't memorize this reference triangle. That would be a really bad idea. So I create the reference triangle. What is this? This is the same as tangent theta equals x over 2. So I create a triangle with this tangent. If this angle is theta, tangent is opposite over adjacent. So let's take opposite to be x, adjacent to be the denominator 2. So this is my reference triangle. And let me create this. Find this hypotenuse. What would be the hypotenuse? It would be 2 squared, which is 4, plus x squared, root of it. That's the hypotenuse. Now let me read what is secant theta. Secant theta is 1 over cos theta and cos theta. Let me read it from this triangle. Cos theta. What is cos theta? Cos theta is adjacent over hypotenuse. So it's 2 over root 4 plus x squared. So this is cos theta. Let me replace it here to find secant theta. It's 1 over 2 over root 4 plus x squared. So it's root 4 plus x squared over 2. That's what we have, which is the same as over 2. Option D. This is the same. Root 4 plus x squared or x squared plus 4, they are the same, over 2. Okay, that's how we use reference triangle. Now let's do the activities. We have 2 activities. The first one should be simpler. And the second one is the one that I mentioned. If you just rely on the formula, you will stuck. You can't solve the problem. Let's do the first one. I look at this. The term that grabbed my attention is this term. More particularly, this term. It's a number minus something squared. Which of the identities is 1 minus something squared? Those three identities, one of them is 1 minus something squared, the other one is 1 plus something squared, the other one is something squared minus 1. We have three identities. So which of them is 1 minus something squared? That was 1 minus sine squared is cos squared. 1 minus sine squared is cos squared. So I need to do the substitution sine. So I need to substitute sine theta. But not if I do just sine theta, that's 4 minus. Recall that I first need to factor this 4. Then after factoring 4, this becomes 4 minus 1 minus x over 2 squared. So x over 2 should be sine theta. X over 2 should be sine theta. In other words, x should be 2 sine theta. That's the thinking process that I get this substitution. If you like, just use the for memorization, use your memory that, oh, I have a squared minus x squared. That's a squared minus x squared, where a is 2. So I need to do the substitution according to the table. When you have a squared minus x squared, you do the substitution x equals a sine theta. So my substitution is x equals a is 2 sine theta. Both of them is fine. But it's better to understand why we are doing this. Okay, good. Now I need to do the substitution. To do the substitution, I need to replace everything. That term is clear. X, I replace it with this. For this one, I need a computation of derivative. dx equals 2 cos theta, derivative of sine. d theta. Now I know how to substitute this. I know how to substitute this. I need to substitute that. To substitute that, you can do a computation that I mentioned, factoring 4. Then you have 1 minus x over 2 squared. Replacing this, you can either first factor 2 or first substitute this. It doesn't matter. If you want to find the substitution, you need to first factor. But when you have the substitution, you can just substitute. So when you substitute this, you get 4 minus 4 sine squared theta, and then you can factor 4. Let's do these computations on the next step, all of them. So I have 16 over x squared. X is this, so it's 2 sine theta squared. Root 4 minus x squared, which is this. 2 sine theta squared. And then I have dx. dx is this. Let me write it here. dx is 2 cos theta d theta. That's dx. Okay, let me simplify it. First, I have this 16 times 2 cos theta over dt. This is 4 sine squared theta. And this is after factoring 4, it's root 4 1 minus sine squared theta. It's 4 minus 4 sine squared theta, which is 4 factored 1 minus sine squared. If you further simplify this, you get numbers, you get 16 times 2 cos theta dt over 4 sine squared theta. This one, using the fact that this is cos squared theta, you get root 4, which is 2, absolute value cos theta. But do you remember? You don't need absolute value in these kind of computations because of the domain that we took for theta. So basically I get this. Now I can simplify. 2 cos theta cancel 2 cos theta. 4 cancel 16 and you get 4 out of it. So at the end, if you simplify, we get 4. Let me write 4 on the back, or yeah, let's write 4 on the back, and then sine squared 1 over sine squared theta d theta. That's what you get. This 2 cos completely cancel this 2 cos. This 4 cancel 16 and you get just extra 4. Write it on the back. And then 1 over sine squared. Or if you like at this step, you can write 4 inside. 4 over sine squared d theta. To compute this integral, recall that 1 over sine is cosecant. So this is the same as integral 1 over sine squared, which is cosecant squared. And another thing that you can recall is that derivative of cotangent is negative cosecant squared. So antiderivative of cosecant squared is negative cotangent. So that's the answer. But before moving on to the computation, I ignored all the bounds intentionally. Now I replace them and compute them. But before doing that, let me mention a comment. In the previous lecture, we discussed generally how do we integrate tangent to some exponent, secant to some exponent. The same strategy, the same things apply if you have cotangent to some exponent and cosecant to some exponent. This was very simple. It was just derivative of this. But if this was like cosecant 4, then you could still compute it using this idea of how do we integrate an exponent of tangent and secant translated into cotangent and cosecant. So have it this in your mind that any exponent of cotangent and cosecant, it has a similar strategy to secant and tangent. This For this one, I didn't need any strategy. It was just derivative of cotangent. But if this was harder, like a larger exponents, then you needed those strategy to solve it. That was one comment. Now let's do the substitution in the bounds of integral. So this is x values. When x is 1 and root 3, I need to fill with the correct number that what is theta, corresponding theta at those points. To answer this question, I need reference triangle, the reference triangle that you need to create. You can do that, or you can just substitute and find what angle has that. Uh, let's first do replacing x with 1. Then if x is 1, when x is 1, basically. Okay, good. Then you have 1 equals 2 sine theta. Or hence sine theta, it's 1 over 2. And then you can answer what angle has sine 1 over 2. If you recall, that's 30 degrees in radian. It's pi over 6. So instead of the value theta, I have pi over 6 because sine pi over 6 is 1 over 2. One extra comment, you need to take theta values in this range, not an arbitrary. For example, there are other angles than pi over 6 that have sine 1 over 2, but you can't use any of them. You should use pi over 6 because of these assumptions that I'm in these intervals. What's the problem if you are not in these intervals and you use other values? The problem is, do you remember when we had like absolute value, cosine, absolute value, secant, absolute value, tangent, and we dropped absolute value? That's true under these assumptions, under these intervals. If you choose some other intervals, then it's not true that you can drop absolute value. So if you want to take advantage of dropping absolute value, like we did here, actually, this is after the step, it's not 2 cos theta, it's 2 absolute value cos theta. If you want to take advantage of this, that I can drop absolute value, then you need to make sure that theta values are in the corresponding intervals. So pi over 6, that's what I found. And when x is root free, then replacing in this, root free is 2 sine theta, or sine theta is root free over 2. If you recall, what angle has sine root free over 2, and also it's in this interval, that's 60 degrees, or pi over 3. So theta should be pi over 3. So that's how you change the range of integration. So let me copy those bounds, carry over them over until the step that I did. They are all pi over 6 to pi over 3. At this step, I need to replace pi over 6 and pi over 3 in this. Now I need a reference triangle, because what is cotangent when x is this or that? So you can use reference triangle, or if you can refresh your go back to your memory and say that, for example, cotangent 30 degrees is that, or you can create a reference triangle out of this, which is a triangle where opposite is 1, hypotenuse is 2, and that's theta. And then you can use Pythagorean theorem to find this, which is root 2 squared minus 1, which is 3, root 3. And then read cotangent theta from this triangle. So cotangent theta is adjacent over hypotenuse, which is root 3. Or you can use your memory that cotangent pi over 6 was root 3. In any case, you get minus cotangent pi over 3 minus cotangent pi over 6. Cotangent pi over 6, we already saw it here. It's root 3. And cotangent pi over 3, either using your memory or creating a reference triangle for this. Creating a reference triangle in that case, we have that. A triangle with sine root 3 over 2. So opposite root 3, hypotenuse 2. Hence, this side will be 2 squared 4 minus root 3 squared 3, which is 1. Root 1, which is 1. And that's the angle theta. So now we are using cotangent of theta. So it's adjacent over hypotenuse. Over opposite, which is 1 over root 3. So cotangent pi over 3 is 1 over root 3. Or use your memory. So that's what we get. That's the final answer. If you want, this can be simplified to 8 over root 3. If you take the common denominator between these two and combine them into one fraction, you get that. Now let's do the second problem. This was the first problem. Now second problem. That's longer and needs more computation. So let me do the computation all the way in on the next page. It's integral 1 over x squared plus 6x to the exponent 3 over 2 dx. Okay, that's the one that even if you know the formula, remember that the formula is x squared plus a squared, you may be confused that what substitution I need to do. Because if you didn't understand the reasoning. If you understood the reasoning, then you are good. What was the reasoning? 1 minus something squared, 1 plus something squared minus 1 to create these terms, having these terms. So under this reasoning, I understand that this term x squared plus 6x, let me write it here, x squared plus 6x should be written as something squared. So I should complete the square in this computation. So I need to write it as something squared, maybe plus or minus a constant, something like that. If you compare the terms, I have x squared. If I have a plus b squared, that would be a squared plus 2ab plus b squared. Do you remember the formula? If you want, let me write it here. A squared plus 2ab plus b squared. The idea is to choose a and b such that I have these two terms, but maybe with extra constant term. So I can guess what should be the first term. What should be the first term? It should be something that it squared should be x squared. What squared is x squared? It's just x squared. So that's x. Now that I have A, I can find B. What should be the next term? It should be something that twice of x times that question mark is this term. So I know that 6x should be twice of x times question mark. So then what is the question mark? The question mark should be just 3. If if you can write 6x as 2x times something, that thing is 3. So I found that the next term should be 3. Good. I created the squared terms that I want. Now it remains to find the rest of the constant. These are, of course, not equal. What is this? This is x squared plus 6x. I just matched the first two terms out of them. But plus second term squared, 9 as well. But I don't have any 9 there, so I need to subtract 9 to cancel these two 9 to get the same thing. Or if you like, here I plus 9 minus 9, and then I have that. Good. I'm almost done with the guessing what should be the substitution. Let me keep this here. So now I'm in the form of something squared minus a number. So I'm not in these forms. I'm in this form. After factoring 9 out of this, after factoring 9 out of this, you get x plus 3 squared over 9 minus 1, which is exactly like this, what I want. Not exactly, it should be something squared. So let me bring this 9 also inside to have it x plus 3 over 3 squared. Now it's exactly like this. It's something squared minus not any number, just 1. Good. What was this identity? This identity was secant squared minus 1 is tangent squared. Do you remember? That was the identity. So this suggests me that I need to do the substitution this package, which is something squared, that package is secant. So x plus 3 over 3. So I do this substitution. This x plus 3 over 3 should be secant theta. In other words, x plus 3 should be 3 secant theta. That's the substitution that I should do. Good. Let's do this substitution. So I get first dx. If I take derivative from this equation or take differential from this equation, dx equals derivative of 3 secant, it's 3 secant tangent, and then d theta. So this dx term is 3 secant tangent d theta. Now I should write this, but let me take advantage of this computation that I did up to now. I checked that x squared plus 6 is the same as this. So x squared plus 6 is the same as 9 x plus 3 over 3 squared minus 1. I already did this computation here. And I'm substituting x plus 3 over 3 with secant theta. So replace this with secant theta. What do I get? I get the whole thing to the exponent 3 over 2. That's this. Inside it, I have 9 parentheses secant squared minus 1. That's what I get. That's the substitution. Now use this identity. The whole point of using this substitution is this identity. Secant squared minus 1, it's tangent squared. So this is tangent squared. So I get first considering 3 over 2 as a root and then exponent 3, that's the same. Exponent 3 over 2 is the same as 1 root, that's 1 over 2, and 1 exponent 3. If you consider it like this, 9 tangent, what was it? Tangent squared theta 1 over this. I wrote this so huge, so let me write it smaller. 1 over this cubed. Okay, and the rest that I had. Now it's easier to simplify. What do I have? Root of this 9 tangent squared is free absolute value tangent. Free absolute value tangent. But recall that I don't use absolute value because of the assumption on the domain of theta. So it's just free tangent theta to the exponent 3. Which is simplify. This is tangent. This is the same as 27 tangent cubed theta. So when you simplify 3 and 27, they simplify to 1 9 in the denominator. So I have 9 in the denominator. Tangent and tangent cubed, they simplify as 2 tangents in the denominator. And I had one secant that is just there and nothing happens to it. So that's the simplified version. Let's continue the computation of this on the next page. We had this. How do I compute this integral? It may look like exponent of secant and tangent, but tangent is in the denominator. So it's better to write it as write everything secant and tangent in terms of sine and cosine to get to see what do we get. We get 1 over cosine theta, that's secant. It's 9. Tangent is sine over cosine. Sine squared over cos squared. Okay. D theta. Before continuing this, let me explain this. If this was just instead of secant, secant squared, I wouldn't do that. Why? Previous section 7.2, when I have exponent of secant and tangent, and exponent of secant is even, I can use substitution u equals tangent. If this was what I got, I wouldn't do that. I would use substitution u equals tangent because I have even number of secant on top. But I don't have even number of secant on top, so I will write them in terms of sine and cosine to see what do I get. Okay, simplify this. This is this cross multiplying this times this over this times this. So it's cos squared. That's 1 times cos squared. This times this. 9 sine squared cos. Simplifying 1 cos from top and bottom. And moving the 9 outside the integral. 1 over 9 cos theta over sine squared theta. So that's the integral that I need to compute. This one, secant was not even. Again, I'm using 7.2, previous section. Secant was not even, so u equals tangent substitution was bad. That's why I decided to do this. But now look at this. This is exponent of sine and cosine. Again, 7.2. But I have odd number of cosine on top. So u equals sine is a good substitution for this. I do that. So I use 7.2. Using 7.2, I use u equals sine theta as a substitution. Then du is cos theta d theta. So this is du, and this is just u squared. So after the substitution, I get 1 over 9 du over u squared, which is 1 over 9 u minus 2 to the exponent minus 2 du. Good. Now antiderivative of a power term. That's very simple. U minus 2 plus 1, which is minus 1 over minus 1 plus a constant. Is this my final answer? No. The question, look at the question. It was an integral of x. So my answer should be in terms of x. This is in terms of u. So I need to substitute back. What do I get? First of all, in terms of u, that's minus 1 over 2u plus c. Now let me replace back u. That is, how should I replace back u? U is sine theta. So it's 1 over 2 sine theta plus c. Is this good? No, it should be x, not theta. So let's see, how should I replace back theta in terms of x? That's the idea. Secant theta, this was or this one, they are the same. This is the substitution that I did. X plus 3 over 3 is secant theta. Using the fact that, let me use another color. For this, let's do orange. So using the substitution, relationship between theta and x is this. X plus 3 over 3 is secant theta. I need to find what is sine theta and write it here. So how would I do that? Without thinking, definitely reference triangle. So reference triangle. Let me make this reference triangle here. I have a secant, which is 1 over cosine, is this. Hence, cos theta is 3 over x plus 3. That's what we have. Secant is 1 over cosine. It's this. So opposite of this, inverse of this, cos is 3 over x plus 3. What is cos in the right angle triangle? It's adjacent over hypotenuse. So if this is adjacent, this is hypotenuse. If this is adjacent, hypotenuse is x plus 3. Now, what would be this side? This side is root x plus 3 squared minus 9. Minus 3 squared, 9. But that is exactly this, x plus 3 squared minus 9. That is the same as, or you can just keep it as that, or you can write it as x squared plus 6x if you like. That's the same as root x squared plus 6x. You can also find this by expanding this and simplifying. 9 minus 9 cancel. You get that. Okay, good. Now, what do I want? I want sine theta. So that's very simple. 2 sine theta. What would be sine theta? It would be opposite over hypotenuse. The opposite is root x squared plus 6x, that's the opposite, over hypotenuse. Hypotenuse is x plus 3 plus c. So this is the same as minus moving this to top. X plus 3 over 2 root x squared plus 6x plus constant c. And this is the final answer. Note that, oh, by the way, I don't know why from some point I wrote 2. This was 9. So let me correct these numbers. I had this 9 on the back. That was a typo that I wrote 2. That's 9. This is 9. This is 9. And I have 9 here, 9 here. That is the final answer. Note that this is in terms of x. My original question is an integral of x. And the final answer is this. You can do it as an exercise. Take derivative from this and see that actually the derivative is this. So that's a correct antiderivative that we found. So that's this section. Again, I emphasize that don't memorize reference triangles, always create them. For these ones, if you want to memorize them, but it's unavoidable for some questions that you understand the thinking process, that why we are doing this substitution. And the reason behind it is under the identities that we have. 1 minus sine squared is something, secant squared minus 1 is something, and 1 plus tangent squared is something. So you need 1 minus something squared, 1 plus something squared, and something squared minus 1. If you have this, sine will be used. If you have this, tangent will be used. If you have this, secant will be used. And don't forget that this a comes from by first factoring a squared out of this. Okay, that summarizes everything. And have a great weekend. See you next week.